Building envelope, floor walls, or week 11 discussion. We're looking at floor and walls. You can see I have the PowerPoint up here up on the screen. All this stuff should be under content on Brightspace. If you look under week 11, you'll see class notes, PowerPoints, the assignment, as well as this video once it's completed. So the building envelope, chapter 10 and 11 in the book. So you should be reading through that chapter as well, making sure you're not missing any content there. I'm just going to highlight some of them through the notes and the PowerPoints. So we'll get going here. Here's your note package, which you should print off. So floors, areas of concern. So some of these things we've already discussed, but we'll go over them again. Air leakage between sill and foundation wall as well as from floors to floors, so intermediate floors. So an intermediate floor would mean a wall, like a floor system between the first and second floor. So this would be an intermediate floor, so it's between the first and second floor. So how do we treat that? So if there's a rim rack required, it has to be done there as well. So you can see the rim rack was done below. It's also done, if you see my cursor there, I'm on the second floor. So it'll be wrapped from the inside and going outwards, back out and back around. You see here on this slide. This slide just shows the regular rim wrap coming through. They have an intermediate floor along right here. So there's your top plates, right? So it's in between the two top plates, goes out, comes back up, floor system, back onto the floor, and ties up. Okay. So that's dealing with any air leakage through this system. Right? So making sure that we have a good air barrier where there's lots of potential for air leaks. Right? Cold zone between floor joists. So how do we treat that? Is we insulate. So there's a bunch of different options there. Go back to the first slide. All right, so a cold zone in that floor system. So it's either we're using bad insulation there, we can use styrofoam there, we could use spray foam. It also has to be covered with a vapor barrier. So our air is on the outside, thermal, and then we'd have to have a vapor. The vapor doesn't have to be sealed if there's an air. If we don't put an air behind, we then have to seal that vapor. Right? So you can see in this case here, the vapor is sealed. So that's acting as the air and the vapor. Here we have spray foam put in place. That spray foam can also act as air and thermal and vapor. So three functions here. And then we have this picture here showing that the XPS foam is sealed with spray foam. So that should be further out. You see the foundation wall here, no insulation here at all. Eventually that's going to be insulated. You'd want that foam to be flush with the basement wall. But for now, it's insulated. So thermal, it has vapor and air properties, all of them one cavity. So basically all three of these are air, vapor, and thermal. So that's how we deal with making sure cold zone between the floor joists are taken care of, which is very, very important. A lot of older homes have lots of leakage through the sill plate, and then in the wintertime when it's minus 30, lots of wind, pipes tend to freeze near bathrooms and kitchens where pipes are located close to the foundation wall. So by having a good insulated floor system, you're going to prevent that from happening. Another issue for problem zones, air sealing and thermal problems. So solution, rim wrap, spray foam, or XPS seal. So basically that goes with this note here, cold zone and floor joist. So proper air sealing and thermal problems. One is useless without the other. So if you had just a vapor barrier there, or an air barrier there, and no insulation, it's gonna stop the air from coming through, but it's still gonna be cold. You see a lot in older homes, if you go in and inspect or do a renovation job, sometimes that plastic's not there. It's just simply fiberglass. Um, it acts as a filter. It'll stop the dust from coming through. So a lot of times if you remove that piece of insulation, look on the backside, there's lots of black dust residue. It's because it's missing the air barrier, so air is still flowing through from the inside, right? So even from the outside. So either you have air coming from one side or the other. The key is you have to stop that air. But it also needs the thermal with it. So air sealing, right? So air sealing and thermal will fix the problem. So you need to have an air barrier and you need to have thermal insulation. That thermal insulation in a basement should be something that can accept moisture to a certain degree. So fiberglass insulation in the floor system is not as bad, but preferably you'd like to see a rock salt there. Why? Because lots of moisture in the basement in the summer months. So just keep that in mind. So even here they're looking at air barrier, vapor barrier at partitions. So making sure that things are air sealed and thermally broken. So allowing plastic to go through prior to. So in the framing stages, we have to put plastic behind the stud, right? So if we have a partition wall butting into an exterior wall, that exterior wall needs to receive insulation and a continuous vapor barrier, possibly a sealed air barrier. So in this case, you can see it's sealed, so it's probably a sealed poly approach. But that plastic was put through during the framing stages, which we've already done on the semester 1 project, as well as probably semester 2 project. We would have been getting to that. And then we seal to it. Okay. Another option, which is a pretty smart option, is to leave a gap. You see that a lot with steel stud. This is an exterior wall, so if vapor barrier goes right through, you leave a gap between this wall and that wall to the point where you can actually slip the drywall behind it. So 1/2 inch drywall, 5/8 gap. So that's doing the job of air, vapor. Right, so by allowing the plastic to go through, there's 2 less joints. You see how clumsy this looks? Like that's hard to seal. Most people do this, but it's 2 layers. There's acoustic caulking there, potential for leakage. If we leave that wall away, so like when I tend to do an R2000 build, that's kind of what we do. We put plastic through the entire exterior of the building, then we frame the interior walls after. So it's kind of this effect. There's 2 less joints on the walls as well as 2 less joints on the ceiling. In this case, they're also putting the drywall through, which then creates a really good fire stop, as opposed to having the drywall come in, stop, drywall come in and stop. So if the wood here were to burn, the fire can go through where that stud was. Where if you have drywall behind that stud, if that stud here were to burn, it has to then burn through drywall to get to the next room. Not a lot of people are doing that, but it's definitely a good practice. It's a little extra time, harder to put the drywall through, so that's why people tend not to do it. But that would be something that you have to do if this was 1 unit of a multi-unit plex, and that's another unit of a multi-unit plex. Have drywall go through, maybe 2 layers of drywall to create a fire resistant wall. This is a picture look at the intermediate floor. So thermal bridging at the floor, solutions, XPS on outside rim board. So you can see that here. Yeah, so what they've done here is that could be your first floor walls. It's kind of clumsy. There's better ways to do that, but in this case here, they're trying to reduce as much thermal bridging as possible. So maybe a 2x6 stud. They went with a 2x4 plate, which then allows for 2 inches of foam. So basically using the minimal size of plate possible to allow for styrofoam in front of it. And then you can see the same things happening at the top. It actually shifted the wall out to come in line, which was not completely necessary, but just stays on foam. So they know that this area here is vulnerable, It's very cold. It's a cold zone. Lots of air leakage, lots of heat loss through here. So they're trying to make sure that there's lots of R value there. So they're going from the bottom plate of the upper floor to the top plate of the lower floor walls. And so you can see a little bit of insulation here. They've got the vapor barrier. They've got the rim wrap taking care of the air. We've got this piece of foam on the front, which is taking care of thermal bridging. And there's another foam in front of that that's covering the entire wall. Lots of wood here, right? When you look at your cavities for your walls, not a lot of wood. Get to the floor system, lots of wood. There's your rim board. There's your double top plate. So lots of chance for thermal bridging. So they tackle that by putting another piece of foam there, shift everything in. It's a little more complicated detail, something that you have to think about while you're framing, right? You have to make sure you allow for that. But probably the most typical way would be to still have a 2x6 plate, but they would snap a chalk line in at 2 inches, and that would be where this 2x4 would go. So your top plate would be 2x6, double top plate would be 2x4, and that allows room for that foam to get a really good floor system. So XPS on outside of rim board. So that's another option. I think. Let's see if we find another slide here. Yeah. So this sill gasket. You take the floor and you shift the floor in by the thickness of the styrofoam. So not as complicated, right? The wall's built the same way. When you get to the floors where you have to start thinking. So the floor is shifted in by the thickness of the foam you want to put in place. And then from there, the plywood would go all the way out to the foam. But again, there's a rim board here. It's hard to insulate this area. So what do? XPS foam to take up all that thermal bridging. So then you end up getting 2 layers of foam. So this might be 2 inches. That might be another 2 inches. So you get 4 inches. If it's XPS, that's 4 times 5, so an R20 on the exterior of your floor system. Plus you're probably going to put another R20 back in there with the vapor barrier. So you got the R40 in that floor, really cutting down. So again, thermal's one thing, but you still need to have the air barrier. So in this case, they don't seem to be showing a rim wrap. So maybe the XPS on the outside is acting as the air. So again, not a really complicated thing. Something you got to think about during framing. Shift the floor in. But very efficient. A lot of older homes, when you're sitting close to the exterior walls, you can feel the cold coming from the floor. This kind of a technique is going to help reduce that. The key is to control the air leakage and the thermal problems. So more thermal, take care of the air. Make sure the thermal takes care of the thermal bridging from the rim board, and then you'll get a warmer solution. So that floor, you can see, is actually hanging out. Some people would say that would be weak because this would want to fall. So you're allowed to have the floor hang out 1/3. It has to bear 2/3. So that 1/3, 2/3 rule is something that we talk about quite a bit in construction. So how much wood is left at the top of a rafter when you cut a bird's mouth? 2/3 of the material. Right? So I'll just do a little sketch here. So we see that a lot, 1/3, 2/3. The meat here left over has to be 2/3 of that material. If you're cutting a set of stringers for a set of stairs, same kind of deal there. There's a minimum here, which is 3.5, which is based off of 2/3 of the material. Okay? 2/3 of the material. To me, 3.5 is not enough. 5.5 is a better number, but it's again associated to the 2/3 rule. You can take away 1/3, leave 2/3. 2/3 of the material would be best for strength. You can see right here, wall can overhang floor by 1/3 of the bottom plate width. There's other options out there. So rim board with incorporated foam. So it's a fairly new product. I've never used it, but I think it's a good product. So it's an insulated rim board. So it comes pre-insulated. So one less step. Whenever you nail that rim board in place, there's already foam put in place. Let's see if we can find that right here. So they kind of sandwiched a piece of EPS foam between your standard rim board and then OSB sheath. Obviously the thickness of this is fairly large, so you got to keep in mind that your floor joists need to bear on the sill plate by a minimum 1.5. Right? So you might have to jump your sill plate up inside, maybe go to a 2x6. I don't know if they have a picture of this. Or you'll have to put joist hangers. Right? So if you're not bearing enough, see here, that's probably 1.5 inches. You see this looks like 1.5 inches, so that looks like the same, maybe a little bit bigger. So that's fine, that'll work. You just got to keep that in mind. If you're going to use an insulated barrier or insulated rim board, is there enough room for it? So we kind of backtrack here, look at a few of these. There's another option, drawing basically just like we were looking at. So here they're showing 2 sill gaskets. A sill gasket and a termite shield and another sill gasket. Pressure treated sill plate, foam board, wall is shifted out. 2x6 frame wall may overhang rim joist by up to 2 inches. Okay, so 2/3 rule. And then foam on the outside, we got damp proofing, protection board, probably cement board. But again, taking care of the vulnerable areas. You see a bead of silicone or sealant here. A lot easier to do that while you're framing the floor before you put the plywood down. And put a bead of sealant there. Try and get in there later. It'll be hard to get to do a good job. You won't be able to see what you're doing. Where if you did it from overhead, fairly easy to put a bead caulking there. So our acoustic caulking would be the best product there. Again, here you can see lots of acoustic caulking. It comes in a tube. A little messy, but it does a good job. You can see they have it everywhere between layers, right? Is it necessary? So if I have a good air barrier, sealed 100% on the outside, are these beads necessary? No. But a good idea. Okay. Let's see where we are here. So balloon framing. Wall from sill plate to the underside of the truss. So balloon framing, you see a lot in older homes for stucco, but you're starting to see it come back around again for efficiency. So let's just see if we can find here. That's your standard balloon framing. They wouldn't be doing it this way. By doing it this way, you're actually allowing for the floor joist to come through and nail off to the side of the studs. And then there's a ribbon, a leaden ribbon put underneath. All of that is taken away from insulation. It's adding to the thermal bridging effect. So what they actually prefer to do is to put a ledger board. So 6mm poly goes through, so insulate 6mm poly, and then a ledger board screwed on, or so screwed on would be structural screws, or nailed on, or lagged on to these studs. Keep in mind, fire stops required every 9'10" max on a balloon frame structure. This is kind of the effect right here. There's your balloon frame structure. You see there's 2 plates here. So that might not be there on a balloon frame structure, but it's an intermediate floor. So it's the floor between the first floor walls and second floor walls. As opposed to having those floor joists run in, you put a ledger board. So first you have to have plastic behind that ledger board. So a little bit above, a little bit below, to make sure you can tie into the 6mm poly on the upper floor, 6mm poly from the underfloor. That ledger gets nailed on, screwed on, lagged on, whatever the case, and then joist hangers for the joist to sit into. So what that's doing, as opposed to platform framing, we just looked at platform framing being very hard to insulate. If you look at all the meat here, all the wood here, lots of wood that are occupying an area where we could have good insulation. So if we go with the balloon frame, we're not interrupting that space. Like if this was a balloon frame, those 2 plates wouldn't be there. There'd be a stud here, and there'd be a stud right over here. So we'd be able to get proper insulation into that area, proper vapor barrier into that area, proper air barrier if it's on the inside, and then our floor goes in later. Right? So we're trying to not interrupt the systems, right? So the air, the vapor, the thermal. And again, we could have our foam on the outside. So this is, looks like it's coming out of the foundation. It's similar, as opposed to having platform framing, where the floor goes underneath the wall and the wall sits on top. Balloon framing has the wall come all the way down to the sill plate. So again, why is that good? Insulation all the way down, so creating a thermal break between each stud. We'd want to then create a thermal break on the outside with continuous insulation. But for now, at least you have a thermal break, so we have the ledger nailed on. So in this case, it doesn't have to be necessarily lagged on because it's sitting on top of the sill plate. But it's not interrupting all the important systems for insulation. We still have to have our 6 mil poly draped through. Ledger goes in, joist goes on. No hangers required here because it's sitting on top of the foundation. And then keep on working from there. You can see they added a row of blocking here, which compresses the insulation a little bit. But that's for backing for drywall and for moldings. I think you could probably get away without putting that blocking there, but some people might throw that in there to make sure that the baseboard has something to nail into. If your studs are 2 feet on center, probably a wise idea. If your studs are 16 inch on center, probably not as important. But again, a lot of people will put that in. In my opinion, sometimes less wood is better, again, for thermal, right? You're not compressing that insulation. But if you get you put a 3/4 inch piece of material there, that wouldn't really affect anything. It's if you try putting an 1.5 inch piece of material in there where you start to compress the insulation. So you can buy strapping that's 3/4 inch by 5.5. That would be perfect for that location. And then you just basically nail it in almost with a brad nailer or a stapler, almost could even hold it potentially. Here's showing some engineered floors, balloon frame kind of a scenario. They got a ledger down here, and then floor joists going into kind of like a rim. So they use the TGI as a rim. Walls go through, so it's a double frame wall. The inside wall is going to carry the floor. So again, we get good insulation. Right? We need good insulation on the exterior walls. This scenario down here is basically we went to a passive home 2 years ago, and it was done this way. So the walls are platform framed. Notice no lintels. No lintels over the windows. So if you have lots of windows facing south, for example, as opposed to having a lintel above every single window, what you could do is put the lintels up in the floor system. So basically the lintel goes from one end of the building to the other end of the building, transferring the weight down through each stud. So pretty smart system, because if I have a massive lintel here, it's hard to build up insulation in that area. If I have a floor system, I can build that insulation all the way to wherever I would like. So I could probably bring the insulation in an extra foot if I wanted to, as long as I wrap that properly to air seal it. With a wall, I'm limited to that 5.5 inch cavity. Well, if I could put foam on the outside as well, but imagine if I can over insulate that floor system, I can then get maybe my R24 easily, if not trying to exceed that to make sure that it's warm. Okay, so that's a pretty good idea on a wall with lots of windows. Eliminate the lintels, have the floor carry the weight through all of the studs. You still see there's point loading occurring on the sides of the window, so a double stud. Here they got a triple, probably just for spacing, and then again a triple at the far end is kind of what I'm thinking. Joist hangers on all. Okay, so the actual beam is carrying the weight, not the wall per se. So that beam is being supported by these posts. So not a bad idea. ICF homes are kind of done that way as well. So with balloon framing, that's ICF here. These are the ties. So I think every 16 inches there's a ties. That's where you can actually screw into. If you're putting this kind of a system, there'd be actually a metal bracket poured into the concrete. So whenever the concrete is still pliable or wet, that bracket would be put in place, or be put in place prior to, then you pour the concrete around it. And then you bolt the ledger. So this is the ledger. It gets bolted onto that bracket. So that's a pretty good system. And you can see right here, there's your ICF, foam. There's brackets there. The ledger gets bolted onto that, so it's thermally broken, right? We have a piece of continuous insulation on the inside, a piece of continuous insulation on the outside. The floor goes into that. So it seems like it's weaker, right? But like construction, having something sit on top of something is always going to be better because you're fighting gravity. If you did this kind of system, right? So if you do a ledger, you're always fighting gravity. If I put the floor on top of a foundation, gravity is basically neutralized because it's sitting on top of an object. So it's a little more difficult, but as long as you're using the proper fasteners and proper anchors, it's a really good system. So balloon framing on an ICF, perfect scenario for eliminating thermal bridging. And then again, not necessarily to insulate this area, but again, some people might add more insulation there, make sure it's nice and warm. But there's probably about 3 inches of foam here and 3 inches of foam here, or maybe it's 2 inches of foam. That'd be 4, yeah, that's more. So more than likely from outside to outside is 10. There's 2 inches here, 2 inches there, and there's 6 inches of concrete, lots of rebar in there. So you can see they're going to go with this place. It's going with a double wall. So really trying to make sure that it's nice and warm. This here picture just talks about fire blocking. Wall plates act as fire stops in platform framing. So if we don't have, so these plates act as fire stops. So if we don't have those plates, such as balloon framing, we have to have blocking put in place to stop that from occurring. So the top plate, bottom plate act as fire stops. If fire were to get in between these two studs, it travels upwards, right? The heat's going to travel and burn that top plate out. So that top plate's going to slow down the fire. So that's basically what it's doing. It also helps with strengthening the wall. So if I had a stud from here to here balloon framing, and I put a load of blocking in there, it stops the fire from traveling through, but also gives the wall more integrity. So it won't fall apart. And takes longer to burn through, so less likely for the stud to collapse and the building to collapse. SIPs. Okay. So structurally insulated panels. I think that's a little further down there. But, so we talked about that. Another method is having continuous lintels around the perimeter. You see a lot of passive homes. Big windows, they want to get heat gain, right, on passive houses. So they want lots of solar gain. So they have lots of windows allowing heat to come in and heat up the space. Therefore, it's a good option to get rid of those lintels. So we can over-insulate the floor. So no lintels required in the walls. Membranes have to pass through prior to installing. So depending on what you're doing for air barriers, you got to make sure you think about that at that stage. Would require lots of exterior insulation to reduce thermal bridging, so you'd have to have some insulation on the inside and on the outside to get rid of the thermal bridging. SIPs. So move on to SIPs now. Structurally insulated panels, also known as a sandwich panel. Panel products that have EPS foam in the center and are sandwiched by 2 layers of OSB, so it comes as a unit. And you can see it could be used for roofs. You don't see it a lot used on a roof panel, but it could be. So maybe that's a cathedral ceiling room. You see this is also a cathedral. So they're going to put a SIP panel on top of that as well. They've already put the SIP panels here. But it's taking care of basically your framing stage, your sheathing stage, your insulation stage, your air barrier, your thermal. So it's like a one-shot deal. You're achieving lots of systems. So labor costs are reduced by quite a bit. They're using long structural screws to screw things together. So there is thermal bridging. So the bottom plate is a 2x6. So, and basically the SIP panel is hollowed out by 1.5 inches at the bottom, 1.5 inches at the top, and by 3/4 on the sides. So basically the SIP panel slips over top of a 2x6 and it gets nailed through the sides. There's usually a little batten that goes in between. You see the foam here is cut out to receive a 2x6. That'll join this panel to the next panel, which then also receives a 2x6 vertical. So half of it goes into this panel, the other half goes into the other panel, and it gets locked together. You can see kind of happen here. There's a plate across the bottom. You see the gap it's sliding into. There's a 2x6 nailed on already. This panel is going to be lifted into it. How does wire running through that? They'll take a router. The router will actually cut through the OSB and through the foam. They can also use a heating gun to then run wires horizontally. They try to avoid running wires horizontally. They try to come up through the basement. So if I need a plug here, I'd come up from the basement to that plug, then wire back down, go over, back up, back down, go over, back up, back down. Standard houses, the wires, you'd have a box here, and you drill holes in this direction and run the wire from that plug to that plug, and then you'd run wires from that plug to that plug. So SIP's a little different, just down, over, up, down, over, up. So the wire has to be continuous, right? So it has to go from this plug. So we take the wire from here up to the plug, back down, continue, up to the plug, back down. A little extra wire, but you're not reducing the thermal in those SIP panels. Here you can see the long structural panels going into the plates. So there'd still be a top plate. You see there's a 1.5 inch gap at the top of each SIP panel. Eventually we'll receive a top plate. You go back to the previous slide, there's a vertical stiffener in the middle. So a block of wood, not all the way down, to then nail your top plate into. So pretty good system. I've worked on one of these. I didn't actually put up the SIP panels, but I did the trusses on them. So they had the entire foundation done with the SIP panels. The SIP panels in the basement were thicker. They were 8 inch in width. And then the upper floor panels were 6 inches in width. So the basement was like a preserved wood foundation. We talked about that in the previous chapter. So the footing underneath the SIP panel was a 2x12, I believe, preserved wood, not pressure treated. And then they had the SIP panels treated with preserved chemicals. So they were all green. And that was their foundation. So it was homeowners did it themselves. I think it took them a while to get to the stage where they needed trusses. But then they called me in to do the trusses. So we had a good look at the building. We had to fix a few things on the top plates, making sure that they were nice and straight there, but pretty good system. So the thermal bridging was very, very much so decreased because of the panels. You still have the odd spot wear at the joints where it's going to be cold. So maybe another layer of foam on the outside would not be a bad idea to get rid of that thermal bridging. They even made a, so that if you don't want to do a balloon framed with the SIP panel, which is possible, a balloon frame allows it to go through, they made rim board out of the same kind of thing. OSB foam in the middle. Floor is sitting on top of the foundation. So there's a foundation, thicker, upper wall a little bit thinner, and then a 2x4 wall for the rim. So again, trying to get as much thermal into those walls as possible. So you can see sealing between things, very crucial. So seal between layers. So drywall, not drywall, the floor sheathing gets sealed to the top plate gets sealed to the SIP. That 2x6 piece that falls in between gets sealed to the sides of the OSB. So lots of caulking to be put in place prior to dropping down membranes. But it's a system. Cantilever floors. All plywood edges glued to create a vapor barrier. So basically your plywood floor that extends out, if there's any joints in that plywood, so I have a joint right here, you'd have to put glue in between that joint and then seal it, because that's the vapor barrier. Whenever we look at floors and walls, you have to treat a floor just like a wall. So it needs a vapor, it needs thermal, it needs air, and it needs moisture. So normally our vapor barrier is on the warm side. So when you're talking about a floor, a lot of times your plywood becomes your vapor barrier. There's enough glue into it, as long as we glue all the joints, it can then turn into a vapor barrier. Some people, I've seen some people put vapor barrier down on top of the floor joist and then drop their plywood on top of the poly. Then, to me, you're not getting a good connection between your subfloor and your floor joist. You're not gluing your subfloor to your floor joist, so there's potential there for squeaks. And every time you put a screw through, you're putting a hole through that barrier. Where if you do with the plywood, you put a screw through the plywood, it's somewhat sealed. Right? When you put a screw through plywood, it kind of turns its way through and somewhat seals it. And then let's say you go put hardwood flooring on top of that plywood. Every time you put a staple through the hardwood flooring, it punctures through the plywood, and then it would puncture through the 6mm poly. Well, the 6mm poly is not fully attached to the plywood, so it could go down by pressure and have air leakage through those staple holes. You usually put, you can see right here too, sealed subfloor. All the joints are glued, and you're gluing the plywood to the floor. Okay, so that's going to be your vapor. Then we thermally insulate that. In my personal opinion, anything that's a floor should be spray foamed, just because of, again, moisture. You get lots of ladybugs in there, lots of flies in there. So if you have something that's not going to be able to allow insects and rodents to have a spot to nest, would be more beneficial, but more also the moisture. Any moisture, let's say I have a foggy day, a lot of that moisture can then make its way up into this insulation. So it should be air sealed. So that shouldn't happen, but it might if somebody breaches the system. So maybe spray foaming that area before you install your finishes. And it would be a good idea. If not, rock salt. Okay, would be a good idea. But the key is, this is very vulnerable. That's a floor. So the R value in a floor is going to probably be closer to an R30. Again, if you check SB12, depending on the package, that number might change. But I believe R30 is a pretty constant number for insulated floors. So not as much as a ceiling, but more than a wall. Okay. Again, a lot of people will put a layer of styrofoam underneath here, which helps with air leakage, helps with thermal bridging. Okay, so vapor, thermal, some kind of a barrier here to create the air and the moisture. Okay. So here's an example with styrofoam. So 1.5 inch styrofoam under the plywood, then bats, and then more foam. You see the ceiling where the red dots are. Spray foam here. Okay. So they're using this foam as the air. Sealing. So it's sealed to plywood, sealed to rim board. That's showing typical. So that's like a soffit here. So a lot of houses built, 20 years ago or so, they have the cantilever on their floor, they put fiberglass bats into it, put soffit over it, and that's it. So there's not a lot of thought put into building science. So what's stopping the air from getting here? So that's like going outside with a sweatshirt on a windy day. Are you going to be warm? No, that's only the thermal. It's missing the air. You need the windbreak. So the windbreak is not on, so you have lots of air leakage. This is going to be a cold floor. So the thermal would have did a good job if it would have had stopped the air leakage. So an air barrier to stop the air leakage. Some other kind of layer to make that a little warmer due to reducing the air leakage. This is showing a, as you can see here, the notes here. All plywood edges glued to create the vapor. Insulate cavity, spray foam best option. Air seal underside of floor to prevent air leakage. Very important, right? You need to control air leakage, otherwise it feels cold. You can put all the insulation in the world into a cavity. If you don't control the air leakage, it's not gonna warm up. And the best way to think about that is, like I said, put a sweatshirt on. That's your thermal. Walk outside on a windy day and cold day. Are you cold? you feel like you don't have a sweatshirt on. But throw on a windbreak, and next thing you know, now it's working. And the thermal insulation is warming, stopping your heat from leaving your body, basically. And then the air barrier stopping the cold air from zipping through and going through the insulation and making your body cold. So the insulation needs some kind of a air barrier to stop that from the wind from blowing through. So the best thing is floors need to be treated like a wall. Vapor, thermal, air, moisture. Right? Just because it's a floor doesn't mean there's no air going to reach the underside of it, especially if it's a cantilever floor. A cantilever floor could be from the second floor walls. Right? It could be coming out over top of the first floor walls, and the second floor walls are sitting on top of it. So lots of wind pressure coming in, hitting the wall and bouncing up. Just kind of go back to that slide, right? The wind hits here, and up, up. So this floor would be really cold if not done correctly. This would be maybe in a garage. So let's say we have an insulated floor, so a garage down here potentially, living space above. For forever, these rooms above garages have been freezing, just because of it's a hard area to insulate, right? So a lot of people are now realizing that they have to make sure this is airtight, first of all for combustible gases, and toxic fumes, but also to keep things warm. So we have to have insulation, we have to thermal break it, and we have to air seal it, first of all for no air coming in, for making things cold, but also for gases from the car if you start your car in the garage. So heating ducts in those floor systems are kind of a problem, but you have no choice. You want to get heat into those rooms. The key is it has to be air sealed down here to stop gases from getting into these pipes, which basically throw heat and air into your rooms. So the air sealing across the bottom has to be bang on for the rest of the systems not to fail. You can see adding extra foam below a duct. So as soon as you put a duct in place, you start compressing the insulation. So again, whoever's insulating, want to make sure that you're doing a good job here. If you compress the insulation in this area, that insulation is not doing anything, therefore there's lots of heat loss there. So these cavities probably better suited for spray foam. So you can spray foam underneath here first and then kind of work your way out with the spray foam. Spray foam in here first and then work your way out. A lot better results, more cost, but better efficiency. So if you have a tight budget, maybe just spray foam these areas, right where the ductwork is, and then the rest fill with bad insulation, and then follow with continuous insulation, and then air sealing. Okay. Here's some typical floors that are insulated. You can see fiberglass insulation, the paperback. So that paperback is acting as the vapor barrier. So they have the vapor barrier facing up, which is correct, because that is your warm side. So vapor barrier facing up. They could have used the sheeting as their vapor barrier, but they decided to put the paper. So maybe they're looking at using two products. So not a bad idea. Right? And then again, they'd have to follow with some kind of a air barrier. So a lot of people, when they're doing a ceiling, they'll put the insulation in and they think they have to put poly here. If they put poly on the underside here, they're now trapping moisture. Vapor goes on warm side, right? So where this guy's standing, he's in the cold part. So it's kind of the backwards way of insulating. So you have to make sure you really, really understand what you're doing there. Where does vapor go? Vapor goes on the warm side. And on the cold side, we have to then stop moisture from going in and possibly air. This is an example of a crawl space, poorly done. I've been in a lot of crawl spaces, basements, and these people don't have the know-how. There's a duct going through, insulation is poorly placed. That would be perfect for spray foam. Okay? But what's missing here is basically a moisture and air barrier. They've poured concrete here, so probably reducing some of the moisture from going up into the wall or up into the floor. But this insulation is acting like a sweatshirt on a coldy day with no windbreak to stop it. Any moisture from the ground going right into that insulation. You can see it's breaking down. There's all kinds of dust in the fiberglass. What's that caused by? Difference of pressure, right? So if I have difference of pressure between inside and outside, that means I have air movement from inside to outside. So dust from here is traveling inwards, and it's getting collected by the fiberglass insulation, acting like a filter. Where if I had a barrier there, that barrier would catch that particle and not clog up the pores on the insulation, making it not as effective. You can see at the far end, insulation actually falling down. So at bare minimum, what they should have did is put a strapping probably every 2 feet to stop the insulation from falling down. I would put tar paper first and then strap it. That would have been bare minimum. So tar paper on the underside of a crawl space is not a bad idea because it's acting as a moisture barrier. Maybe the plywood floor, if glued, is acting as vapor and air. Right? So you're not having to worry about putting membrane on the underside and sealing it around everything. You're just trying to stop moisture from getting in. So tar paper overlapped would be a moisture barrier. We don't have to tape the seams, but that would stop moisture from getting in. That would also help to hold up the insulation. And on top of that tar paper, maybe a strapping every 2 foot on center, just to hold everything up so it can't fall down. Okay. The best scenario, spray foam. For like, if this entire floor could be spray foam, would be ideal. Right? Same as here, spray foam. So if you can afford it, that's a spot where it's well worth it. Making sure that you're air sealing that, you're also sealing it for gases. But again, very, very costly. But if you're up in that room when it's really cold outside, you're going to appreciate the warmth. The last thing you want to do is be uncomfortable. Feel like you need to have a blanket on. Every other room in the house is comfortable. You don't need a blanket. And all of a sudden you're in this room and you're feeling drafty all the time. So spend a little money extra on that foam, and then it'll be there for a lifetime. Okay. Floors over cold zones, we kind of looked at that. Most time plywood seal at the edges creates a continuous airtight seal. Also, vapor and air could be use of bats and rigid insulation to eliminate thermal bridging. Kind of look at that over the garage. Air sealing is important to prevent carbon monoxide from entering the home. So making sure it's well air sealed. So probably a layer of drywall on the bottom of that, and one coat of mud is required to create the fire protection for a. So if we had a room above a garage, the underside of that floor would have to be first of all vapor. You need thermal, air, moisture, and then you need to have a fire protection. So a layer of drywall and one coat of mud on the seams, so paper tape and one coat of mud minimum to create the fire protection. So here, insulating and sealing the perimeter walls goes with this slide. Perimeter walls insulated, best option is spray foam. As you can see here, plastic is put down first, and then they spray foam. So the spray foam will actually hold the plastic in place. See here, the spray foam to the concrete. Here's a concrete footing with a post to a LVL beam. Well, they spray foam the perimeter of that concrete, then hold the plastic in place. All the perimeter walls are spray foamed. They spray foam the footing, they spray foam all the floor system. So that's better than spraying between every single floor joist. So they're actually going to heat this space. They'll try to keep this space warm. It keeps the floor warm, as opposed to insulating between all the studs. So this is a good idea, probably the best option in my opinion for a crawl space is spray foam, perimeter walls, maybe even putting a layer of foam on the floor if the budget allows. If not, maybe an XPS foam, tape all the seams. So underneath that, preferably gravel, then maybe your 10 mil poly, and then the foam on top of this gravel, let's say. As you're crawling around, your knee's going to crack the foam because it's not perfectly level. By spray foaming a thin layer on the entire bottom surface, that won't happen. Right? Doesn't look as pretty, probably cost you a little bit more money, but you're going to spend quite a bit of money on the XPS sheathing to cover this entire floor. But as you crawl around under there, you're going to break little pieces off, and then it's just not as good. That piece gets shifted, it's losing some of the R value. So spray foam under this area would probably be the best, on the floor and on the walls. So floor meaning the mud, not up here. This is the old-fashioned way of doing it, right? So you frame up a 2x4 wall in a crawl space. Looks like there was a change of plans here. They had to cut up the floor, put in new footing to support this beam. Maybe this floor was sagging, so they went in and put a new beam in, footings. So cut out the slab, which is probably only 4 inches thick. They probably dug down below the slab, maybe 12 inches or more, depending on whatever the engineer required. Then poured that footing and slab at the same time, and put the post on, and away you go. Foundation walls are just fiberglass with 6 mil poly. So pretty common, but not really the best products. As you can see, it's basically full coverage insulation right to the plate. Fiberglass, which is going to absorb moisture, but it's common. Like any house built 10 years ago, that's the way they were doing it. Right? Fiberglass in the basement, 6 mil poly in the basement. So my opinion should be rock salt with smart paper retarder nowadays. But pretty typical if you go into a house to see this kind of a thing. That you don't see a lot of this occurring. Just too expensive. Probably the way people should be going on. Okay. Crawlspace is again perimeter walls insulated. So we talked about this a little bit in the last chapter, but so this is a crawl space. Not a very lot of headroom if the floor was on. So small little addition more than likely. So taking care of the styrofoam. See, there's styrofoam on the ground. So if you walked on top of that, if it's not perfectly flat underneath, the pieces will crack. So if you do a really good job of raking it out, foam might not crack as much. But putting all that styrofoam down is a lot easier to do before the floor goes on than after. So taking care of all this insulation when you have lots of room to move around, it's going to be a lot faster, more efficient than doing it later. How would you bring those sheets in through a little crawl space hole? Right? So it's a lot easier to do it ahead of time. There's just something we already looked at, but the kind of like the thermal barrier with aluminum, and then your wire mesh with radiant heating tubes for radiant flooring heating. Okay, so hot water will circulate through the pipes. He's tying the pipe to the wire mesh. So that's just a tool to spin the wire. So walls, advanced framing, things that are going to add some potential for energy efficiency, so increased stud centers. So the most common way to improve efficiency on walls is to change from 16-inch on centers to 24. So that's almost a given whenever you're going to get into advanced framing or passive homes, or trying to build a house that's going to be a little bit warmer, is increasing your centers, more insulation, therefore warmer building. Structural members, joists, studs, and trusses need to align. So if you're going to do that, you can see the alignment. Studs right over top of floor joist, right? So all the way up from the ground. So joist, stud on top of joist, joist on top of stud, stud on top of joist, truss on top of stud. So all your members have to line up. So you got to make sure you do your layout from the same corner for all your components. Like, it's easy for us to see all these pieces aligning right now because they removed all the material. But during construction, you got to pay attention to that. You should be able to see a row of nails on the plywood to know where the joists are. Make sure your studs line up with that. Otherwise, it's not allowed. You can see here they went with a single plate. So a single plate. So that it becomes even more important to make sure everything's aligned. Okay. So single top plate, no headers on non-bearing walls. So you see this is a gable end here. Gable end is basically a truss. The truss carries from this point to that point. So they didn't actually put a gable end there. They actually put a regular truss, which is good because it's going to carry the weight. Well, no lintel here. There's a lintel here. All the weight of these trusses are bearing down on top of them. You can see they put little metal brackets here. So metal brackets put in place to act as jacks. So eliminating the jacks here by using metal plates. So instead of having a king and a jack, they have one single stud with a metal bracket designed to carry the lintel. You can see they added another 2x4 on this side of it. That's just backing for trim. and then stack frame 24-inch on center. So here's another picture showing studs 24-inch on center, so fairly wide apart. But then they go and put 3 studs in the corner here. So go to the effort of putting 2 foot on center studs, and then this piece of wood could have been eliminated right here. See how they have the studs right underneath the rough sills there? Why is that there? Especially if you're trying to get more insulation in your wall, right? You go 24-inch on center, you're saving money on studs, but you get more insulation in. Well, don't go put a stud on either side of that rough sill. When the window gets installed, the window gets screwed to the sides. The window is hung off the sides. It doesn't sit on the rough sill. So the rough sill doesn't have to carry the weight of a house. It doesn't have to carry the weight of a window. So don't put wood where it's not necessary. Nails will perfectly hold that rough sill in place. And then once the drywall goes on, you're going to screw drywall screws every 8-inch, probably around the perimeter of that, maybe every 12. So you probably have a drywall screw here and a drywall screw here. Well, drywall is somewhat structural, not really, really structural, but it does help with rigidity. It stops things from twisting. So that'll hold those 2 pieces together. So there's no need to put that 2x4 here and that 2x4 here. That's just taking away insulation. You can see in the corner there they used an L, same way as we did in the shop. Right? That's called an energy efficient corner. It's become standard in the industry, but it was first put in place to help with corners being cold. Right? There's still a lot of wood there, but better than what it used to be. Here's again the stack effect, right? Stack framing. Studs on top of floor, studs on top of floor, truss on top of stud. Transfer plates right through, then we go with a single plate. The single plates would be locked in with metal brackets. Okay, so if you're going to go with a single plate, 2 pieces joined together, they'd be bridged over with a piece of metal. Place openings to fall between the on-center studs to avoid extra studs. Okay, that's not really what this is about, but what this picture here is showing, conventional framing is in yellow, advanced framing is in dark green, advanced conventional framing is in green with diagonal lines. So basically, how many studs are you saving? So if you go with the dark green advanced framing, so you got 1, 2, 3. I guess there's one here, so 4, 5, 6, 7, 8, 9 studs if you went with advanced framing. Conventional framing, 16-inch on center, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So quite the difference there. And you can see minimizing the lintel here. Get no lintel there for some reason. Maybe it's a gable end. So cripples. There's 2 cripples here. There's only 1 for advanced framing. Advanced framing, you can see they're allowing for insulation. So instead of putting 2 studs and trying to fill that gap with insulation, they're creating a ladder. Or again, the 2x6 on the flat is an energy efficient way. So the way we do it in the shop, 2x6 on the flat. Instead of going with 2x6, you could go with a 1x6 to get more insulation in that space. And the key is insulate later, so it doesn't get wet during construction. So quite a bit of savings just on material. But the key is more insulation. Like you see, every time there's a stud there, there's less spot for insulation. Everything gets a little bit tighter. Here's basically a diagram showing placement of windows, trying to follow where the studs are located. So instead of putting a window over here in the middle of these 2 studs, shift that window over so it aligns with the stud. So the stud becomes the king, and then you got your jack. So you're then at least eliminating a stud here. Right? Instead of having a stud over here, it means you still have to have a cripple here, a cripple here. So trying to work with the spacings. Some people even go to the extent of making sure that the windows are exactly fit in between stud component. Instead of going with 36 inches here, maybe go with 4 feet. So the window's a little bit bigger. But at least you're then eliminating this section of stud. That'll be gone. But there's a point load there. So here we didn't require a point load because it's sitting on top of the floor joist. Unless that's a TGI, then you'd have to block either side of it because it's not strong enough to carry the weight. But if that window was bigger and hit this one, that would pick up the weight. It looks like TGI, so it'd have to be squash blocks on either side of the joist to carry the weight of the window. There's a perfect example. That window's placed in between two studs. Look at the gap. Not much insulation can go on either side. 2 squash blocks are required. So the window's where it needs to be, potentially, for the plan. But it would have been more efficient to have it hit a stud location. A lot less wood, right? We eliminate the jack here. We eliminate the squash block. If we made the window bigger, we eliminate the jack on that side as well. It's trying to minimize the amount of wood, if possible. And another thing is having windows on 2-foot intervals. Right? So having the window either 2 feet, 4 feet, 6 feet, so that it lands on both ends. Okay. There's the plate. So single plate tying onto a single plate, but that could be the same plate used if I had a joint right here. So if I had a joint right here with another 2x4, that plate would be what we would use to tie the two together. So just a plate connector. Also shows instead of putting a stud there or backing there for a drywall, you can use clips. So metal clips screwed into that stud, drywall will go against that. And you just float the corner, meaning no fasteners in the corner on the one side. Which sometimes prevents cracking too. It's not a bad thing. Float in the corner. So this sheet of drywall on this wall would be screwed in regularly. This sheet would have been the first one to go in, so that goes on first to hit that bracket. That goes in second, gets screwed in regularly. And then whenever you tape the seam with mud and paper tape, it'll hold the two sheets together. So this sheet that's not screwed will then follow this sheet. So if there's any movement on this wall for some reason, it'll follow that wall, reducing cracks. If you had a kid running into the wall at 100 miles an hour and hit that corner with his little bike or something like that, it might crack the corner, but it might crack higher than 9'10". Possible. A lot of room above the windows. And there is a sheet here, so that's from here to here is 8 feet. And that might be 16 inches. You can see the joint on the plywood here. And then they have plastic on top. So air barrier is probably on the outside. Plastic on top of the plates. More than likely the air barrier is the house wrap. One thing else we see here is, just make sure we're covering all this as we're going through. Frame wall, single top plate, joist studs, and trespass line brackets installed to lock the joint. Look at that. Design wall length to fit size and material available. So that was on the previous slide there. We'll just go back. Design wall length. I guess it's not really on that, but so try to have walls, buildings, to be 2-foot intervals. Try not to have something at 23'7" or 23'6". So you have to cut things. Try to make sure that we're not wasting material first of all, and then 2-foot intervals so that things line up. If we're going to have 2 foot on center as our spacing, let's make sure our walls line up with 2 foot on center intervals. Lintel size correctly, so if 2x6 lintel is all you need, avoid placing a 2x10. So I know in the first semester, my brain is set up for speed whenever you're talking about framing, so I kind of do the opposite, right? I use 2x10 everywhere. But that's not energy efficient. Energy efficient when you're putting the minimum size lintel, so I can then get more insulation. But the problem is it's more work. So that means all your jacks potentially are different lengths. So let's say this was a 2x6 lintel, that one there is a bigger window and it needs 2x8. Maybe this one's a really big window and needs 2x10. Well, the jacks for all of these windows would be different if the lintels were up at the top. Jacks would be the same if the lintels were dropped. which is kind of what you want for energy efficiency, having the lintels dropped. If the lintels are all the way up at the top of the wall, what you're doing is creating lots of thermal bridging, lots of potential for heat to escape. I just kind of do a cross section of the wall. There's your stud, double top plates. If I go throw a lintel, which is more of a speed thing, right at the top, then I have very little insulation here, and that would be a window, versus maybe dropping the lintel. If I drop the lintel down, I have a stud there instead. Maybe put a block of wood there instead. Now I can actually get R value here. So on a house, that's your roof. This is our area where insulation gets compressed, right? We have insulation coming in, and all of a sudden it gets compressed. And we have venting here. So if we have this effect happening, a lot of heat can escape there. We have wood here, wood here, wood here, wood here. Very cold. Where if we have this kind of going on, maybe just a single plate down, because we're doing advanced framing, there's less thermal, therefore less heat loss entering into that vulnerable area where the heat gets easy path going through the insulation that's compressed, right? And then that creates ice damming. So we get hot air coming through, melts the snow, and then it freezes. And then the next day, same thing, melts the snow, and all of a sudden we have water here. Now that water starts traveling up the shingles, going underneath and then getting into the structure. So by looking at energy efficiency again, dropping the lintels, you can see almost on every single picture on energy efficient, the lintels have been dropped. Right, so lots of insulation here. Single plate, lintels dropped, good R value. So we're not getting a thermal mass of wood here, which stops which doesn't stop the heat from leaving. Okay. So here again, a good picture, not necessarily the clearest, but you see your floor joist are traveling this direction, which means this wall's carrying weight. This one, not so much. Still carrying weight, but not so much. You see here the windows fall 2 foot on center, so 2, 4, 6. So they lined up one side. So now they're minimizing cripples. No lintel there because it's not needed. Over here it's 2 foot on center again, but probably maybe from the other side. But studs are 2 feet on center. The window doesn't quite line up, but they have a lintel here because that's carrying the weight of the floor joist. So it's stacked framing. Joists line up with studs. Joist lines up with studs. Only putting lintels where you need to. Okay. Avoid having lintels and gable end walls unless necessary. We just looked at that. Options for lintels. So 2-ply, 2-by materials sandwiched together and placed towards the outside. That's exactly what we do. 2 lintels sandwiched together, placed towards the outside, which then allow for insulation after. Box header. So this is an LVL. So instead of going with maybe 2 2x10s, they might have gone with 1 LVL maybe with a small window, therefore getting more room for insulation. So it's a stronger piece, and therefore more insulation. What I don't like is they have the rough sill going through and then the jack tying into the rough sill. So the jack should go all the way up, hit the lintel. Again, this plate here, that plate shouldn't be there. Or it should stop here and stop. That side's correct. Oh no, that side's not correct, because there's another window most likely overhead. So that jack should come through and sit on top of the lintel. This jack should come through and hit the lintel. This jack should hit the lintel. That jack should hit the lintel. I have a feeling there's another window overhead there. Okay, so looks like it's an open space. So you walk in the front door maybe. There's a large open space up to the second floor ceiling. So a window below, window above. Maybe the front door is over to the right here. Lots of wood for nothing, right? Lots of wood for nothing here. So cut that out. There's a cripple here that does not need to be here. There's a double here. I don't think that piece needs to be here. Again, another double here. I don't think that piece needs to be here. Just a bad habit of somebody putting a 2x4 to support a rough sill. The blocking here is more likely required. The wall's balloon framed. Okay. Another option for a lintel is what they call a box header. So it's a top plate, bottom plate, and then studs. The key is the sheeting. So the sheeting has to be 15-30 seconds in thickness. So wood structural panels face shall be single pieces of 15 by 32 performance category or greater strength, and then they're nailed 3 inch on center. So 9 inches or 15 inches wide. We can use this application. Plywood on both sides nailed 3 inch on center. What that's going to do is make that plywood part of the lintel, giving it strength. Okay? So 2-sided wood structural. Here's your specs. Nailing pattern. And I guess you can do it with only one side and then drywall on the inside. Otherwise, you'd have lots of drywall over top of plywood. So single stud at sides of rough opening to 40 inches in width. Jack stud required to span is greater than 48, so that's decent. Lots of windows are smaller than 48 or equal to 48. So a single stud, otherwise a large opening, 2 studs. So cripple studs follow the layout. Cripple studs, 1 stud layout, same thing. So framing fasteners per code. So 3.5 inch nails for 2.5 inch material, or 1.5 inch material to 1.5 inch material, and then your sheeting nails would be minimum 2 inches in length. So most people use 2.5s. So fast, efficient. Right? So a little bit thicker plywood, and then nailing pattern a little bit tighter, and that acts as your box header. It doesn't say what the maximum width is though. Right here. So for construction details and maximum span, see the 2012 International Residential Code. So there is specs for how wide you can go. But so again, you're not going to see this on standard construction, but you'll possibly see this on advanced framing. Okay? That's why it's in this chapter. So minimizing lintels, minimizing wood, which then creates path for heat to leave. So another option. So it should be spec'd for spans through the International Residential Code. Here again you can see the lintel, no lintel, right? Another thing is plywood, foam. I talked about this in class a little bit. Instead of using a Bailey T, putting a piece of plywood in the corners. So this might be 2 inch foam. This might be 1/2 inch plywood with a layer of 1.5 inch foam over top of it. So why is that there? To give lateral strength. Stop the wall from racking. Stop the wall from collapsing. Okay. You can see this is a truss style floor joist. So that is a truss going from this point to that point. That's why there's no lintel required here. The weight is bearing here and here. There's no weight there, so no point in having a lintel. Where this wall here is going to have all the joists sitting on top of it. So that's going to have some weight there. But again, you can see 2 foot on center, single plates, you got foam on the outside. Okay. So plywood in the corners to stiffen up. So that's 1 long wall, 1 sheet of plywood. Takes care of that wall. Usually a rule of thumb is 1 lateral support for every 20 feet of wall. Again, that should be spec'd by an engineer, but it's a rule of thumb. Corners. So a lot of people are going with the 2-stud corner now, and then putting a drywall clip in. So what does it do? It allows the insulation to go in and not be compressed. Here, the typical corner we do is we don't have that stud. Some people put that stud in there for backing for exterior finishes. Not really required. And you can see what it does to the insulation. So some people think backing is more important than insulation. We could put a thinner piece of material there, but again, I've never put a piece of wood there, and I put on all the types of sidings. Never had a problem. Most sidings require strapping, so just go for wider strapping. But by putting that blocking there for exterior finishes really cuts down your insulation. So we typically do the L corner without that piece. But that being said, it still compresses the insulation. When I install the insulation into a corner like this, I normally cut a piece to fit from here to here to here to here. I install that piece of insulation first, then I cut another piece to fit from here to here. So when I cut a piece of insulation, I oversize it by 1/2 inch. Same thing here, oversize it by 1/2 inch. Put that in, then I put this second piece in after, avoiding the insulation having to do one of these curls that is being compressed here and doesn't look very good. I like having my insulation touch to 6mm poly. You see them here being used on the ceiling. Sometimes they get used on the ceiling because you want to float the drywall to prevent truss uplift. So you can see it happening here as well, and then you have them in the corner as well. Okay. So it gets screwed onto these holes, you can see right there, and then the drywall slips into it. There's these two little teeth here. So once the drywall slips in, it has trouble coming out because it catches on these two teeth. Okay. So that eliminates studs in a lot of locations. Right, that's potentially an exterior wall, interior wall butting into it. Normally we have backing there. So instead of having backing there, we now have just drywall clips, and then we can get our proper insulation, proper barriers through, no interruptions. Okay. And once the drywall's taped, it is very strong. Again, you can see it here. So 2 insulated, so again a single stud on this wall, single stud on this wall, no corner backing, drywall clip. So drywall slips in, drywall goes on top. So the clip goes on first, this sheet goes on second, that sheet goes on third. Okay. Again, exterior wall, interior partition, drywall clips, no backing. Drywall clips. You can see the odd horizontal blocking. So clip goes on, drywall goes in place. There'll be another clip on that side, drywall will go into place. Okay. Eliminating backing where we're going to be compressing insulation. Exterior foam increases R value, reducing thermal bridging, keeps sheathing warm, preventing condensation. So we looked at all that stuff. So having continuous insulation on a wall is almost inevitable nowadays. So the key is some way of stiffening up the wall. So there's a Bailey T going from top plate to bottom plate, which is crucial. You don't want to go from stud to stud. You wouldn't want to go from here and stop it here, because that stud will deflect. You want to go from top plate to bottom plate. So it's a kerf, and then you drop the Bailey T into that kerf and you put nails top and bottom. Okay. If there's a window in place, so we have to do this on our smaller walls in the shop because we were putting styrofoam on. We had a door, so what we did is we kind of went from same idea, from a double. So we had a king and a jack, which is solid. We went on an angle from there. So we squared up the wall, tacked it down so it was nice and square. Chalk line, cut, drop the Bailey T in, and then remove the wall from the floor. Later we'll put styrofoam onto it. Another option is a lead brace. We talked about that in semester 1. Lead brace, so notch to allow a 1x4 to go in place. That's lots of work. Bailey T is kind of the way to go. So here you can see the Bailey T in place. You can see backing here. See this company here put backing for the exterior for probably a bigger trim. So maybe they're going to have a 3.5 inch trim on the exterior of the window, so they want to make sure there's nailing there. Again, nailing into sheathing is fine. They're really worried about the finishes. Then you're reducing your insulation. They went with just a king. So there should be a metal bracket here which you can't really see, but could be put on afterwards. Another thing they're doing here is a staggered wall. You see the bottom plate looks like a 2x8. top plate looks like a 2x8, and they have a stud on this side, and then a stud on that side, stud on this side, stud on that side. So essentially what's happening there is they're weaving the insulation through the plate. So the plate's probably 7 1/4, and it might have a stud here, and then a stud here, and a stud here, and a stud here. So they'll be able to weave the insulation through the wall, reducing thermal bridging without continuous insulation. So basically there's no continuous path through the wall other than the plates. Okay? And some people will do that at the plates. Actually have 2 plates at the bottom, which is called a double stud wall, which we're getting to shortly. Double stud wall. So there's just the foam sheathing on the wall. There's showing the wall with the sheeting in the corners, foam coming off of it. How do you treat the foam in the corners? So normally it's flush to flush, then you put a little piece in the corner. Otherwise it screws up all your layout. Right? If you lay out something for 16 inch on center or 2 feet on center, typically that goes from the frame. So that's where you want to start your foam from to make sure it lands on a stud. So in this case they have OSB sheeting, so that's what's happening in the corner there. That's what I was talking about before. This is probably 2 inch foam. Then they went with 1.5 inch foam with a sheet of 1/2 inch or 7/16 OSB, making up the 2 inch. Right, so that's a 2 inch block, which would be representing this. So they fill in the corner with that leftover blocks, and then they seal that with a loose skin product that's compatible to the foam, so it doesn't break it down. And then there's a large trim board, so they flared it out with foam. And then you can see they have the corners basically created like an L, the way we kind of do it, right? I don't put that piece in place, but the reason why they put that piece in place is for this nail. This nail has something to go into. So if you're putting foam on your wall, that backing could be required. Otherwise you'd have to have a big piece of strapping, which is fine as well. So moving away from that, so increasing our value. So a few different ways here. Single stud wall with an interior strapping. This one here is just putting continuous. So single stud wall with exterior insulated sheeting. So that's your simplest format, which we've been talking about for weeks now in building science. So single studded wall with exterior insulated sheeting. That's becoming the norm, where it used to be an advanced framing technique. Now we kind of have no choice, but you see they're adding a second layer at the floor system, which we talked about, and then a continuous layer on the entire perimeter of the structure. Okay. That's probably your simplest form, bringing the wall up to possibly an R28. Okay. So if we had a 2x6 wall at R20, 2 inches of foam on the outside, almost R30. Okay. So we're going to increase the R value on the wall pretty simply by adding foam to the exterior. What are the consequences of that? Making sure our wall can breathe, which we've discussed quite a bit. Here is a single studded wall with strapping and insulation. Okay. So the key there is minimum penetration. So you can see the first wall is maybe a 2x6. That's where the poly is installed. Okay. And then from there we have strapping going horizontally. The strapping is pretty big, 2x3, or maybe even 2x4. And basically all our wiring is run through that wall. So the outside wall is always going to be bigger because we need more insulation on the outside. You can see here 2/3 insulation on the outside of the vapor. That's the vapor. And we have 1/3 of the insulation on this side of the vapor, which is okay. And all the insulation, all the wiring is on the warm side of the vapor, which is kind of ideally what you'd want. That way there's no conduction through metal wiring. So I've done a lot of houses this way. So normally this wall would be framed first, and then you'd insulate, poly, and then frame the second wall, and then do all your interior partitions afterwards. So then the trades could come in at that point. You can see the rim wrap occurring here though, for this assembly. tying into that vapor barrier, which is in the middle of the two walls. 2/3 insulation outside, 1/3 inside. But the key is, if I have any wiring, any switches, they're not affecting my barrier. I don't have to come back later and fix a bunch of areas because the electricians put holes through it. They can just simply go in the basement or from the top, drill a hole down, bring the wires up. They don't have to travel horizontally if they don't want to. They can come from the bottom up. Okay? So you can see here, barrier penetration electrical is minimized. Drywall must be installed vertically because of the membranes going. But that's not necessary, but it's just easier to put the drywall on vertical with thin material to fasten to. But it's no worse than a stud. We look here, double stud exterior load bearing wall. Double stud exterior load bearing wall. So it means the outside is load bearing. Inside is not load bearing, just receiving finish. Again, there's a separation between the two walls. So we have a wall framed here, which is receiving vats. Then we have insulation in between the two walls, and then another wall framed. So that's where your barrier is. Your barrier is actually stapled onto the backside of those studs. And then another layer of vat insulation in that wall. Okay. So you can see thermal broken between two walls. The wall's very, very thick, so you're going to get a high R value here. Very high R value. Thermal broken throughout. Okay, so the key, you see where the poly is? The poly is closer to the inside. So there's more than 2/3 to the outside. Not as much on the inside. So you can't have too much insulation on the warm side of the vapor, otherwise you're going to cause a problem. You don't want that vapor to be too far to the outside and get cold. You want that vapor barrier to stay hot. So if you only have a little bit of insulation in front of it, not the end of the world. But if you put too much, now that vapor barrier could get cold. If it gets cold, it condenses is the problem, right? So if we have heat loss, we have cold coming in, it'll condense. If we don't have that much insulation on the warm side of it, condensation won't occur. So you could do some calculations to figure out, basically that's your sheathing. That's your sheathing, where will the dew point occur? Just showing thicker walls, not really anything to do with a double wall. I'm not sure why that's folded in there, but they're using floor joist here for studs. So trying to get a greater R value. The plates are rimboard. You got lintels in place. You're just getting a bigger cavity. Okay. See these lot in passive homes where they actually build their own studs. So they have a 2x4, 2x4, and then they have plywood sandwich in between. Okay. So they're able to get rock solid in between those gaps, as well as in between these trusses, if you will. Okay, so same thing with plywood, and then again a bigger gap in between. So you can see they have sheathing on the exterior already put in place, and it's all taped. So that's air barrier on the exterior. Okay. Here's another system. So bottom plate is OSB sheathing. 2x4 wall on the inside, 2x4 wall on the outside, and then you get your top plates. See the windows are framed up. No lintels over top, so more than likely the lintels are going to be in the floor system. Massive depth for insulation. Okay. So lots of R value. So you're going to insulate between the studs, you're going to insulate between the two walls, and then again in between the studs. You have sheathing on the exterior. You can't really see how they're going to finish the wall, but they might finish the inside wall with OSB sheathing again. Here's another one from our notes here, double stud interior load bearing wall. So now the interior wall is load bearing, and then it actually extends out and is supported by a diagonal ledger, which is lagged into the foundation. So this is good for retrofitting this kind of a system. Have it extend out a secondary wall, and then insulate that area. Okay. It could be done on brand new construction as well, but it's just a different look. So a lot of passive homes do is basically this. They'll actually have the wall stick out. Underneath this wall would be OSB foam. So like maybe an 8-inch. That's probably closer to 10, maybe 10 inches of foam on the foundation to then make the foundation warm. And then make it look like it's all continuous. There is again the side view of it, angling up. Kind of looks weird. So if that went down right to grade, it would be a lot bit better. But there's ICF foundations that look this way. When they have a brick ledge, they'll curl out to support the brick. So it's a common look that you're starting to see on ICFs, which then would make it somewhat easier to accept. Okay. But again, just overloading insulation. Insulation in between the sides, insulation in between the walls, then insulation in between the inner studs. Again, vapor barrier is on the back side of the interior wall. Making sure that running wires and all those things are not becoming an issue. It also makes sure that, again, metal's not being conducting the cold to come in. Standoff walls, so that you can see here, this is a wall being stood off the foundation. So very similar to the previous one, but now there's no bracket holding onto it. So over insulating to the outside. Again, good retrofit. You see there's a couple of brackets that get nailed into the trusses. So meaning this wall was framed up, trusses were put in place, and they're doing that after the fact. So it could be retro, renovation, or that's part of the plan, just doing it afterwards. So the wall, if you will, is being hung off of the truss system. These are the small battens, which then are supporting the exterior, which will receive finish. Okay? So around windows, massive window bucks. So they're calling them window boxes. But they're not carrying any weight. They're like a cosmetic wall put in place to receive finishes and basically insulation. So not a lot to them. So, and if you're going to build a house this way, it has to be engineered. You can't just decide, okay, I'm going to put a 2x2 here, 2x2 here with 1/2 inch plywood. The engineer has to spec this, make sure it's correct. I'm going to pass code. They probably even have to look at modeling to see how efficient it's going to be and make sure there's no problems with the system before you can go ahead and build. But this is passive home stuff. Okay. But again, almost a balloon frame, right? Balloon frame going through, ledger or floor onto the balloon frame. Steel frame must use insulated exterior sheeting to prevent thermal bridging. So if you're going to have a steel frame structure, it's all stud steel, you then have to treat it like a commercial building and have all your insulation on the exterior. You still put some on the interior, but you need a majority to the exterior. Okay. I don't think I have much on that, but so standard steel frame must be insulated, thermal bridging. Yeah. The wall will get wet, count on it. How fast the wall cavity dries depends on permeability of the sheeting, the cladding system, number of joints in the sheeting or the cladding, orientation of the wall, length of drying season, relative humidity, and outside air. So a lot of stuff that we've kind of looked at already. So one way to kind of deal with that is drying behind the cladding, right? So cladding is your siding. So we showed this slide before where we have tar paper on the wall, we have strapping, and then a metal mesh or could be insect screen at the bottom to allow water to get out, stop insects and rodents from coming in, and allow air to flow through and dry out that space. So second plane of protection. So vinyl siding is not waterproof. Cantilever siding, not waterproof. Brick, not waterproof. James Hardy siding, not waterproof. That's your first plane of protection. Water will get through that. We caulk some of those joints. But majority of the time, we kind of accepted that the first plane of protection is not watertight. Water will get behind that, so we have to make sure we allow a space for water to get out using a second plane of protection. That has to be probably the most detailed one, where we cannot allow water to go through. So you can see here, there's tar paper. We got the strapping, You see this type of siding here, they require tar paper behind the joints. So Maybach siding would be done that way. So that's your first plane of protection, is your siding. Second plane of protection is the tar paper. And then we have a buffer in between, so strapping with gaps to allow water to get out. You don't want to have water trapped between tar paper and siding tight, because then it works its way through the staples. It's under pressure, so it's almost forced to stay where it is. It can't fall. Where if you create a gap between the two products, it allows it to come out. Also allows air to flow up into it to dry it out. Okay. So here you can see a mesh across the top to stop the insects as well, I believe, and then they put a strapping on top of that. But there's our insect screen at the bottom. That's probably the most typical. I like this, but not as available as screen, but this would be 10 times better. Rodents wouldn't be able to chew through that. This could probably easily be manufactured. I mean, you wouldn't need holes here on the backside, but you need holes across the bottom. You almost make that yourself out of aluminum and then drill a bunch of holes into it. Make sure the holes aren't big enough for certain insects to get in. Could be time consuming, but better than the wire mesh where an insect can kind of go behind it and work its way in. Should be taped here, but still insects can eat through the tape. So the metal here a lot stronger and sturdy. But this is minimum code. You can see the same thing over top of a window screen. So strapping's all vertical. Never horizontal strapping. If I go put a horizontal strapping on top of a window, the water gets behind the siding. That strapping is now going to hold the water. So that's the common thing that people want to do when they have a window. You look at the apprentices, they did it. They put strapping around the entire window first, where you should have verticals only, so that when the water hits, follows the house wrap, gets onto the drip cap, and then comes out of the building. Not trained properly, that's what ends up happening. You never want to have a horizontal strapping that can collect water. You're allowed to run strapping on a 45-degree angle, but you shouldn't be putting it onto a wall horizontally. I have a couple pictures from a couple slideshows ago that had horizontal strapping on the wall, and that's a no-no. It holds water. Water sits on top of the strapping, finds a way to go through the nail holes. So even across the bottom, it should always be vertical. If the distance between here and here is too great, I put a vertical piece in between. Small little vertical piece, maybe 2 feet long, as opposed to a horizontal piece across the bottom. People have to think. We're not putting wood in place necessarily to install vinyl siding. We are, but we have to make sure we don't trap moisture while we're doing it. So don't put a piece of wood in place until you've thought about, is there any dangers there? And the best way is just to keep things vertical. Keep water running downhill. If you're stopping water, you got to find some way of getting that water out. So if you're stopping water on top of a window, you have to find a way to get that water out. If you're stopping on top of a ledge here, see right here, this is what they call it's called a water table, but they have a drip cap out of wood on top of it. So any water collects, hits that drip cap and comes out. Any horizontal member has to have a way to get the water out. Okay, otherwise it'll trap. So you would never ever caulk between this siding and this drip cap, the wood drip cap. The bottom of that would probably have a curve, but you don't want to allow the water to come out of there. So if you caulk that, now water's trapped. Okay. Looking at, make sure we got all this covered. So kinetic energy. So movement of water through cladding is basically what that is, right? So kinetic energy is water in motion and wants to continue in its path. Those basically water moving. So we want to try and stop that water from moving. So here's looking at, so large overhangs can help protect walls from rain. Momentum carries rain through openings. So a lot of times, this is not really the best example, but this is looking kind of at brick. This is looking at a batten from overhead, trying to close off those gaps. But the best spot we can look at that is on a roof or over top of a window, where water is kind of coming down, even on this drip cap. So water would flow down here If we don't have this metal bracket, it could just kind of curl and stay. But you see how this here's your drip cap. Water will follow that drip cap, gets to the edge of it. It wants to curl around, but it's nothing to grab onto. There's a gap there, so it falls. So if that's making contact, it would just curl back around onto that material and possibly go uphill. So capillary action occurs with cracks or openings that are 1/32 or less in width. So if we create a larger gap, that won't occur. It's hard for the water to wrap around and continue up in the direction. But it's got momentum, it's got speed coming down. If there's a spot for it to grab on, it'll grab on. So that's why we want to have our drip caps away from the cladding. This is just looking at pressure, wind pushing in, forcing water to go in. So creating a bigger gap behind products allows for the water to drop, otherwise it kind of gets caught and immobilized and then slowly wants to work its way in. We're going to have a larger gap with good flow. It's easier for it to come out. Water just flows out. Okay. So pressure from positive, negative, from inside to outside could affect the building. So having a gap in between with good ventilation allows for airflow. It's kind of the same thing as a gas can, pouring gas out of a gas can. Right? If you release that valve, allowing air to be behind water, it pushes the water out or pushes the gas out. Or if you seal off that cap at the back of the water can or gas can, it kind of bubbles out, if you will, struggles to come out. So that's kind of the same thing. If I have a tight space with no airflow behind it, the water has trouble flowing out. Where if I have a good open space with good air coming from behind it, it'll force it all out. It's not trapped, it's not holding onto it. These are looking at pressurized versus unpressurized, so simple rain screening, and then pressurized, equalized rain screening requires vents and cladding. So this one here is, so that's the top view looking down. You get your corners. So here they're showing only having one spot where air can come into, so it's kind of like a negative pressure. One spot where air can come into, so negative pressure. And this side here actually has two spots, so air flowing through, coming through and wrapping around and taking all that moisture out. That could be a good thing. So sometimes having a vented cladding system is good because it will take any moisture out of there and pull it out. What you don't want to have happen is all that moisture go into an attic. So here you can see two spots on the wall where air can flow out horizontally as opposed to going from the top up. So one spot actually just kind of neutralizes the moisture, so it's kind of stuck there. Two spots allows it to flow and get out. Okay. So having a strapping across the top would then make it kind of like a negative pressure. So it's kind of a neutral, and so it's not really well ventilated. Right? So basically it's going to take a little while for that to dry out because air goes in, it can't come out. If air goes in and is allowed to come out, you'll get good airflow. It'll travel through there quickly. But if air goes in and hits something solid, it's kind of stopping. So that's kind of like a negative pressure. But you don't want to leave that top open because air can actually go right into the attic. So what some people do is they leave gaps on the strapping in these locations to allow the air to flow through. Kind of create like a loop. So it can move from one cavity to the other, allow for some airflow to come through. 3/4 inch battens, 1x3 or 1x4. So a lot of times 1x3 in these locations, at the corners, sometimes even a 1x6. So it says here battens pressure treated. I've never used pressure treated strapping. That's something you'd want to look into. It's stated here, and that's probably from the manual. But make sure that pressure treated wood doesn't affect the siding you're using. Right? Maybe pressure treated wood might eat the tie deck. Who knows, right? So before you'd ever use pressure treated batten on a wall, verify that there's nothing in that pressure treated wood that will affect the finishes. So house strap goes on first. Strapping would go on after the rain screen. So rain screen would be put in place. Drip cap, if you wanted one, would be put in place. Then the strapping goes on. Same as over top of the windows. So house wraps on, windows put in place. You peel back the paper at the top, put the drip cap on. You see the end dam here. Then the strapping would go on last. So probably screen there as well. So a piece of insect screen, then strapping, then curl up your insect screen, staple it off. Make sure we've covered everything here. So movement of water, so kinetic energy, water motion solved by changing direction. So kinetic energy running down, so if you have a windowsill, a lot of times, so if this could be a brick house, there's your mortar, another brick, there's your window. Water comes down, hits, curls around, that would be a cut on the underside of a windowsill. Whenever water hits that cork, water then drops. So that's kind of how we deal with kinetic energy around a building. So water in motion has momentum. If that cork wasn't there, the water could go right in between here. Okay? But by having that, it hits that spot and then drops. Blocking the pathway, so stopping water from getting in between materials. So maybe a bead of caulking here would also prevent that from being an issue. Okay? So blocking the spot for water to go in. Drip cap over windows. So drip cap over window goes like that. Curls around. There's your window. So again, same thing, hose wrap, then tape. The water will travel down, come around, hits that edge, and watch the drip. As long as we have enough gap here. So I'd stated in class to leave about a 1/4 inch gap in that location to make sure the water drops. So that's a drip cap over window, and then on a roof, there's our plywood. Kind of goes like that, curls around, out a bit, and there's your fascia board. Again, you got your shingles that go a little bit further, 1/2 inch, 3/8 past. The water will follow, get to that point, and then drip. Usually into east troughs. So east troughs will slip behind that drip edge, curl out like that. The water drips into the east troughs and gets the water away from the foundation. Okay. So kinetic energy on a window, on the drip cap, or on a roof. It's water in motion that's going to continue its path. So a lot of older roofs just have fascia going underneath the shingles, coming down, and then underneath the building. They don't have the drip cap. Then they have shingles like that. They don't have the drip cap. Drip cap is a piece of metal that we install on the building. Looks similar to that. Okay, so that's about 2 inches, maybe 1/2 inch, maybe 1 inch, and then like a 1/4 by 1/4. That gets installed, and then the drip edge is nailed onto the building, and then fascia goes up in that crack. There's our rough fascia, 2x6 or 2x4. And we have soffit put in place, and then fascia board comes below it. So that fascia board here is a finished fascia, is aluminum, very thin. So the top of that fascia is held in place by the drip cap. Okay. Older homes are done this way. So piece of metal bent from here to here to here and follows your roof line. There's your rough fascia. There's your soffit. There's your plywood on the roof. Okay, so that piece of metal follows the plywood on the roof. So water runs around, curls, and goes up here. Potentially. There's no drip to occur. So water under kinetic energy follows the shingles, follows that material right around under just energy. Force, right? It's just energy forces back up. So the way they solve that problem is they put a roof drip cap in place to get rid of that water traveling uphill. Okay? Capillary action occurs, so gaps less than a 30-second. So a 30-second or less prevent possibilities for water traveling. Right? So that's one reason why we put 3/4 inch clear gravel underneath the slab. Is the gaps are large enough in between the rocks that the water can't travel uphill through capillary action. Avoid inward slopes that direct water in. So you see how the sill of the window is out. The angle on the drip cap is out. Naturally, the roof is already sloped, so we have that working for us. Make sure things are angling outwards to make sure water travels down used by the force of gravity. So rain screening, 3/4 inch vertical battens, 1x3 or 1x4. Battens recommend to be pressure treated again. You don't see that, but it's written in there. Weather barriers between sheathing and battens, so the weather barrier should be behind the battens. So some people, when they're building their walls at the framing stage, before they'll stand the wall, they'll put the house wrap on, and then some people even put the strapping on. Some of it, not all of it, to just minimize the work later. The more you can do on the ground, it'll be a lot easier, a lot safer, because afterwards, once those walls are stood up, you're setting up strapping, and then you're having to go around the building doing all the strapping, and then do the siding. So it just eliminates a step while it's down on the ground. You wouldn't be able to do it all, but a majority. It says here corrosive resistant fasteners, so you want to be using galvanized nails, basically, for nailing on your strapping, just in case those nails were to rust, then the rust bleeds out. It could affect your siding, stain on your siding. Insect screen at the bottom of the opening should be metal, so not the vinyl screening. It should be metal screening. Like I said, there's other options out there that could be better. Piece of metal I showed you. 2 types of rain screening: simple rain screening, so air can flow up into the soffit area freely. Issue is that exterior moisture and air can be brought into the assembly, so brought into the attic. That's one problem. So pressurized, equalized rain screening, sealed at the corners and on top. The idea is, if under pressure, nothing will be able to enter, including moisture. So if it's a negative pressure, one hole only, nothing can go in. So that's kind of another way to look at it. We go back to that picture. Where is it there? Right here. So there's 2 ways to look at it. If I have 2 holes open, air can go in there and remove all the moisture fairly easily. And then you're allowing moisture to go in. Again, flow of like a gas can. 2 holes allows flow. 1 hole doesn't allow flow. So that's another good way to look at it. If I have a negative pressure, nothing will go in. Right? Nothing can go in because it's already full. So if I have a glass of water, and basically that's my glass of water, it's full of water. I can't put more water into it. Where if I have a glass of water with a hole at the bottom, the water keeps on coming out, therefore water can continue to go in. So could be a problem, but it could also be a good thing, as long as it's sealed at the attic. Right? If you kind of have this kind of a flow going on, but sealed at the top, wouldn't be a problem. Okay? So they're saying in the textbook that having only 1 entryway is better, because 1 entryway means nothing else will go into it. Only air can come out, water can come out. Okay? So pressurized. I guess that's it. So again, make sure you read the chapter, look through the slides. There'll be an assignment up there as well, geared towards questions from the notes and from the textbook and the slides. So make sure that's completed before our next class.